Greetings and welcome to experiment number 2 of the Mechanical System Analysis Laboratory. The name of the experiment is Steady Laminar Flow in a Circular Pipe, a numerical analysis. So the main objective of this particular experiment is how to write the code of the analysis part when the steady laminar flow takes place through a circular pipe. So these are the contents of this experiment. So first of all, we'll discuss the theoretical analysis of steady laminar flow through a pipe. This part you already studied in second year fluid mechanics subject. Then the second, we will see the numerical approach, how to write the program for obtaining velocity and shear stress distribution across the cross section when steady laminar flow through a circular pipe takes place. So writing the program is the key of this particular experiment. Then comparing theoretical results with the numerical results or the results obtained from the code after execution of the program, and final conclusion. So quickly we go through the analytical part when the steady laminar flow in a circular pipe takes place. We consider a circular pipe having a laminar flow fluid through it. Consider two sections of the pipe, 1 and 2, separated at resistance capital L apart. Then consider the pressure intensities P1 and P2 across the two sections. And we consider the V is the mean velocity of flow through the pipe. Now, in order to investigate the velocity and shear stress distribution across the cross section, we consider a small cylindrical concentric element of radius small r and the length dx. We consider the forces acting on this cylindrical element, that is pressure forces on end faces and shear forces on the circumference. The pressure force on left face, that is pressure intensity into pi r square. Pressure force on right face is obtained by Taylor's expression, that is by incremental change in pressure, that is P plus dabba P by dabba x into dx into area. Similarly, shear forces on circumference, that is shear stress into the circumferential area, that is tau into 2 pi r dx. So if we resolve these forces along x directions, so we can have an equating to 0. Because this is steady laminar flow. So according to Newton's second law of motion, that summation of all forces is equal to 0. There is no acceleration. If we resolve these particular equations, we arrive to the equation of tau. And tau we are getting, that is equal to minus dabba P by dabba x into r by 2. We can call this equation number 1. So from this, we can say that shear stress varies linearly with r, because dabba P by dabba x along y direction or along radius is along y direction is constant. So tau only varies with r. So there is a linear relationship between tau and r. So we can say that tau, when r is equal to 0, which is at the center, then tau is also equal to 0. So shear stress is 0 at the center, and it is maximum when r value is maximum, that is small r is equal to capital R. So tau is equal to minus dabba P by dabba x into capital R by 2. So negative sign indicates that always there is a decrease in pressure along the direction of flow. So that's why the negative sign, because minus dabba P by dabba x has a positive value. Since the pipe is uniform, the pressure gradient will be constant here. And this equation, another equation we can develop in terms of pressure that is pressure head, HF. But this is immaterial as far as this derivation is concerned. We can see the variation of tau with respect to r. It is 0 when r is equal to 0, tau, and it is maximum when small r is equal to capital R. So this is the variation of tau with respect to r. So tau varies linearly with respect to r. So this is linear variation of shear stress with respect to r, maximum at the walls, but 0 at the center. Now the second part, that is we have to develop expression, or we have to investigate the variation of velocity with across the cross section. So for that, we use another expression of tau according to Newton's law of viscosity, that is tau is equal to mu into dabba V by dabba Y. So the same expression we can write in terms of R, because y is the distance measured from the wall. So y is equal to capital R minus small r. So dy is equal to minus dr. So instead of dabba y, if we put dabba minus dabba r, so the equation becomes this. So compare this equation with the derived equation in previous slide. So we get, if we equate this with the derived equation, that is minus dabba p by dabba x into r by 2, we can arrive the differential form of equation of velocity profile. Now in programming, we solve this ordinary differential equation. This is the ordinary differential equation in first order. The same equation we will solve using a Scilab program, which is not that much difficult, even in analytical approach. So here we continue with the analytical approach. So if we integrate this equation, so velocity is the function of only r. So dabba p by dabba x along y direction is constant. So the equation 5 becomes, that is v is equal to 1 upon 4 mu. So r integration is r square by 2. So it becomes 1 upon 4 mu dabba p by dabba x into r square by 2 plus c. Constant of integration is obtained by using boundary condition. So that only one constant means one boundary condition, that is a relation between r and v. So when small r is equal to capital R, that is at the wall, velocity is 0. By using this boundary condition, we can obtain the value of c. And similarly, we can develop expression of local velocity, that is 1 upon 4 mu minus dabba p by dabba x into capital R square by 2. This is equation number 7. So from this equation, we can say that velocity varies parabolically with r. And this is the variation of velocity across the cross section, where if we take small r is equal to 0, then we get the maximum velocity, that is at the center. And if we take small r is equal to capital R, we get the value 0. So that is generally at the walls. So at the walls, velocity is 0. And at the center, velocity is maximum. And its variation is parabolic. So this is a parabolic curve. So we can say that velocity varies parabolically with R. So same velocity profile and shear stress profile we can develop with the help of Scilab coding. So our main aim is to develop the Scilab code in order to get the variation of velocity and shear stress across the cross section. Later on, we can obtain the expression of Vmax also by putting the value of r is equal to 0 Vmax, and we can develop the relation between Vmax and local velocity as well. So that's it for the analytical approach. So the same, we can solve the numerical using this analytical approach. So the same kind of numericals we have solved in fluid mechanics, where when the oil of viscosity 9 poise and the specific gravity 0.9 is flowing through a horizontal pipe of diameter is given 60 mm. Pressure drops in 100 mm length, which is indirectly the pressure gradient is given. Pressure gradient is per unit length. So here it is given in 100-meter length. And determine the rate of flow, centerline velocity, the total friction drag over 100-meter length, the power required to maintain the flow, velocity gradient at the pipe wall, and the velocity and shear stress at 8 mm from the wall. So if we write the given quantities and we convert into appropriate unit, here the pressure gradient is 1800 kilonewton per meters, that is 400 meters. So that is P1 minus P2 is 1800. And if you divide by 100, then it becomes the 18,000 Newton per meter square. Rate of flow we can obtain, but we require P1 minus P2. Length is 100 meter. We can calculate the mean velocity. Then rate of flow we can obtain. The second parameter is centerline velocity, which is maximum velocity. So the relation between Vmax and mean velocities. So that part we have not considered here, but with the help of Vmax also we can mean velocity also we can obtain the Vmax value. Then the total frictional drag we can obtain first by calculating the maximum shear stress which is at the wall multiplied by area. So that is a drag force. And finally, we can calculate the power also. Power is 11.45, that is drag force into velocity. Then the velocity gradient at the pipe wall, that we can again calculate by using the expression of tau max. This is a velocity gradient, and putting r is equal to capital R. So we can calculate this value. So by using this relation, and that is 270 divided by mu, we can get 300 second raised to minus 1. So finally, maximum shear stress that is at the wall, that is tau is equal to 270 kilonewton per meter square. So this is a numerical we have solved using the expressions of different expressions what we have derived. But the same numerical we can solve by using the coding also. The main advantage of code that we can vary the input parameters and it becomes your simulator or a solver. So that is the main advantage of a solver or the programming. So programming help us to investigate the variation of different operating parameters on the performance parameters. So here we are using Scilab for programming. So local velocity also we can obtain here. So that is not that much immaterial for programming. In programming, we are going to obtain the variation of velocity with respect to R, variation of shear stress with respect to R, and the maximum values of velocity and shear stress. That part is we are going to verify during the program. So during Scilab coding for velocity distribution, first of all, we write the input variables. So your initial boundary condition. So the velocity is 0 when R is equal to 0, that is input variable. So at the bottom, we are consider from center line to bottom, towards bottom, we consider the negative values. So from center line towards upward direction, we consider the positive values. So at the bottom wall, when R is equal to minus 0.03, the velocity is 0. So initial condition and input variable we have considered. Then the range of variables. So variation of input variables. So here we are varying the input variable from minus 0.03 to plus 0.03 with the interval. So interval you can change. So it can be even less than 0.001 or it can be even greater than 0.001. But lower the resolution, more accurate is the result. So we have considered 0.001. So if we consider 0.0005, you will get even accurate results. So that you can check by varying the variation of input variables. So these are the variables generally required for ODE solver because we are solving this equation using ODE solver and we are solving first order differential equation. Now, in order to that, first of all, we write all the variables. So, and in some input data as well. So in this case, the viscosity is there. So in the previous problem, the same viscosity we have considered here, that is in 9 poise, we are considering here converted into a Newton second, that is SI unit, Newton second per meter square, that is 0.94 Newton second per meter square. Then second viscosity is 1.5. Then pressure gradient we have considered, that is per meter length, that is minus 18,000 Newton per meter square per meter length that we require. Then we can have this is the relation, that is dabba v by dabba v by dabba r. So this differential equation we have to solve using ODE solver of this. So we can have dabba v by dabba r. So first of all, we write the function. So function that is we require to solve a derivation for v, which is a function of r and v. Then we write the differential form equation on the basis of the equation given that we already derived initially. So that equation is dabba v by dabba r. So the same equation we can write, that is on right hand side here, 1 upon viscosity into pressure gradient into r by 2. So this is the differential form equation that we have written. So function dv and its expression is nothing but the right hand side of the differential equation. So 1 and 2 indicates that is because we are using the different viscosities. So dv, that is one thing. So second, this is the end function. So we have closed this function with 3 we can see the 3-line program. The similar program we can write for the function f2, where for different velocities, then dv is equal to 1 upon viscosity 2. So in that case, 1.5 viscosity will be considered end functions. Then we write the ODE equation, which mainly consists of 4 variables. So this is input boundary conditions, then this is input variable, then this is the range of variable, and this is function 1. So that is for V1. So function 1, we are considering velocity 0.9. And for function 2, we are considering viscosity 1.5. So these are the two solver equations. So now the OD solver will take care of that solution. Then we can develop a plot of velocity versus radius with the marker in this for getting the effect of viscosity 1. We are using the star marker, and for second, that is we are using plus. So 2 plots we can develop, and we can label also. So on x-axis we are considering velocity, y-axis we are considering radius of the pipe, which varies from minus 0.03 to plus 0.03. Then title, we are considering that velocity distribution in the pipe. The legends also we can write Vs1 and Vs2. So this is the plot. If we execute the program, we are getting this velocity profile, which we are not getting in numerical analysis, because numerical analysis only, analytical approach. We are getting the velocity at one particular radius, that is at whether at the bottom or at the center. But here we can get the velocity at each radius part. So whatever the interval we have taken. So now this is the velocity profile for 0.9 viscosity. This is the velocity profile for 1.5 viscosity. So we can see the maximum velocity for 0.9, which we have considered the same data of, that is of numerical data. That so answers are tallied. And if we increase the viscosity, the velocity is reduced. In this case, we are getting 2.5 meter per second. So it is recommended you should take the different values of viscosities and radius in order to get the different velocity profile. So this is the velocity variation across the cross section for different values of viscosities. So we are getting the parabolic profile as usual. So after solving the differential equation. So this is about the velocity distribution across the pipe. The same code we can write for the shear stress distribution. So initial part remains same. So only the part which we require for calculating the shear stress. So we can write the shear stress equation, which is not in differential form. It's a simple equation, Pg into R by 2. So we can take a plot by using plot command, that is R versus tau. And we can labeling also. In this case, x-axis, there is a shear stress. Y-axis, there is a radius of the pipe. And then X title is shear stress distribution in the pipe. And similarly, we are getting this, after execution, we are getting this variation where the velocity shear stress varies linearly, which is maximum at the bottom. That is when the radius is 0.03. And also maximum at the top when the radius is 0.03, but only the values at the bottom is minus, at the top it is plus, and there is a linear variation. So this way we can develop a variation of shear stress with respect to radius of the pipe. So that's it from this particular experiment. It's a small experiment, but we should understand how to write the program for the analysis, a simple analysis of flow through pipe. So here initially we have just refreshed the derivation part of velocity and shear stress distribution for laminar flow through the pipe. Then we have studied how to develop the program for velocity and shear stress distribution, and finally develop a plot of velocity and shear stress using plot command. That's it from this particular experiment. Thank you very much.